In the last class, we saw two parameters z and y parameters. You can see here z parameter leading to definition for current controlled voltage source or trans impedance amplifier it is called. We will call it now in a more general term as trans impedance amplifier instead of trans resistance amplifier. And y parameter, the dual of that, leading to a voltage controlled current source, we called it as trans admittance amplifier instead of the earlier definition trans conductance amplifier. Now, we also understood that these two are more basic than the other two types, and therefore, we can obtain the other two types called current controlled current source and voltage controlled voltage source by simply suitably cascading these two amplifiers. Okay. Now, let us come to the other two parameters which are equally important, H and G parameters we can call. These are going to be having parameters which are dimensionless as well as taking the dimension of impedance and admittance. So, this is normally called hybrid parameter. H is hybrid, G also is the dual of H. So, consider first the independent variables I and V naught now. I and V naught are considered as independent variables and Vi and I naught are then the dependent variables. So, in such a situation we can write linear relationship for these dependent variables Vi as Hi into II. So, this is the H parameter. So, suffix is H I because I is involved with I. This is totally input parameter. This is either self admittance or self impedance, it is called self. Okay. So, Hi is therefore input impedance, dimension is Vi by II. So, impedance when H, that is V naught is 0. V naught 0 means output short circuited. So, this is short circuit input impedance. Hi. Then HR, it is relating Vi and V naught. When II is 0, that is input is open circuited, then if I apply a voltage V naught, how much of it is reflected at the input as Vi? So, this is the reverse or inverse transfer ratio, actually it is a ratio, inverse transfer ratio or reverse transfer ratio. So, voltage ratio, and this is for input open circuited. That is the definition. Next, HF. Once again, I naught and II are related. So, this is a ratio, but you can see here this is obtained when V naught is 0, that means output is shorted. So, this is a short circuit current gain. So, forward. So, this is a forward transfer ratio. This is called current gain or short circuit current gain. Because output is shorted. HF is short circuit current gain, I naught over II. H naught relating I naught and V naught. It is an admittance parameter. Again, it is a self admittance parameter, but at the output. So, output admittance when I is 0, that means input open. So, these are very important parameters, that is why they are so important. We are likely to discuss the amplifier which this parameter normally represents, and what is the amplifier that normally represent? Obviously, you have seen here forward transfer ratio is a short circuit current gain. So, this is nothing but current controlled current source, ideal current controlled current source, which is what is our bipolar junction transistor. Okay. A classic example of this category is bipolar junction transistor. I had mentioned about this earlier, right. This is very nearly equated to a current controlled current source, and H parameters are commonly adopted in defining the performance of a particular amplifier designed with BJTs. So, this parameter is quite a useful parameter because of its close association with a device, okay, which is closely linked to the ideal source that it is trying to simulate. And other parameter which is also very useful parameter which is measured, okay, normally for any device is Y parameter, primarily because these are all short circuit parameters easily measured. It is very difficult to open circuit a practical device. It is easy to short the device. So, this is a parameter which can be easily measured because these are short circuit parameters, and short circuit parameters are practically easy to measure. And these parameters are nothing but admittance parameters, and capacitors which are stray capacitors can be simply adding on to their admittance, okay, as j omega c. So, most of the stray effect is due to capacitors, and that can be simply added to this admittance. So, that is why these parameters are very important parameters in practice, which are measured in most of the designs, and there are a variety of bridges which can directly measure these parameters for any two-port network. Okay. Now, what is the ideal current control current source? Ideal current control current source can be derived from these H parameters, wherein it is unilateral. So, HR is 0, just as we did in other cases. It can transmit only in forward direction, reverse transmission is 0, and HI the input impedance, short circuit input impedance is 0. H output admittance is 0 because it is a current source output, output admittance is 0, and therefore, the ideal current controlled current source can be represented simply by this. Once again, this because this is a hybrid type of parameter, right, mixed type. This is impedance, this is admittance, this is voltage ratio, this is a current ratio. Okay. You should not get confused with this, right. These two are always ratios in these two types of parameter H and G. These two will be always ratios. One is a current ratio, the other will be a voltage ratio. This will be impedance admittance, or the otherwise the other parameter, this will be admittance, this will be impedance. So, let us now discuss the G parameters. There we had Vi and I naught as dependent variables and II and V naught as independent variables. Here we will have Vi and I naught as independent variables. Okay, and this will be in turn representing II and V naught. So, Vi and I naught are the independent variables, and therefore, we will express I and V naught in terms of them linearly. I therefore is equal to G suffix is Gi. This game is now very clear to you, right? You can yourself put down those suffixes. So, Gi indicating what? Self admittance now. So, this is an admittance, input admittance, input admittance when I naught is 0, that means open circuit output. Then G here, what shall I put? I naught and II are related, so it is reverse transmission here. Okay. GR, so reverse what? Transfer ratio, but it is a what ratio? Current ratio. I by I naught when Vi is 0, that is input short circuited. GF V naught Vi, again it is a voltage ratio, forward transfer ratio. So, forward transfer ratio what? Voltage. Again output is open, I naught is 0. Finally, we have this G, again suffix naught, that means G naught, please do not get confused with G being adopted for conductance. These are G parameters, they can be impedances, admittances or ratios. So, G naught is the output impedance with Vi 0, that means input shorted. So, it is short circuit output impedance. So, this is input admittance, but open circuit, right, reverse transfer ratio, but current, forward transfer ratio, but voltage. Now, definitions are all over, except that this G parameter is what is normally going to be giving us voltage control, voltage source. The ideal voltage control voltage source results in Gi becoming equal to 0 Gr. It is unilateral, so Gr is 0, Gi is 0 and G naught is 0, indicating ideal voltage control voltage source block, and it is basically defined by 0 0 0 G. Yeah. This is a voltage ratio. We do not have any device which can really represent this, okay, so nicely as BJT represents the current control current source, but we can make a combination of these devices and obtain a device which is close to an ideal voltage control voltage source. That is the part of exercise which we will be pursuing in most of the lectures in this series. That is, what is our aim in this course of lectures? Basically, we are trying to understand amplifiers and design amplifiers. Okay? Ultimately, these amplifiers should resemble the ideal amplifiers that we want. One of those 4 categories: ideal voltage control current source, ideal current control voltage source, ideal current control current source and ideal voltage control voltage source, which is what we should aim for. Okay? And most of our designs will be spending time on how to put these various practical devices like transistors available to us in such a manner as to design these characteristics for these circuits. Okay? So, this is going to be the aim, and in this process therefore, we should know first of all what we are aiming for. So, this is what we are aiming for, this and here 0 0 0 ZF, 0 0 0 YF. Okay. So, basically we are aiming for these amplifiers. Can we design amplifiers in such a manner that it is close to this, if it is a trans impedance amplifier? Can we design our circuit in such a manner that it can closely follow this, it is a trans admittance amplifier? Can we design an ideal current control current source type of amplifier, or can we get an ideal voltage control voltage source amplifier? Right. So, this is going to be part of what major part of what we are going to discuss in our future discussions. How to coax these various transistors available to us to come close to these ideal. Now that we have studied these parameters Z, Y, H and Z, we can represent any 2 port. In this particular case, we are interested in representing your amplifier by what is called an equivalent circuit. This is what an equivalent circuit is, that this two-port can be represented as a circuit block. How? We know that this is Vi and this is Ii. This is I0 and this is V0. Now, inside, I can represent it as a Z parameter equivalent. Just for example, I am taking Z parameter equivalent. Instead of putting those equations, I will put it in a pictorial manner. That is what an equivalent circuit is. Earlier, we have put down these things in terms of equations, these independent variables, dependent variables, the relationship as a linear relationship in terms of two equations. Instead, now the same thing will be represented as an equivalent source or an impedance or admittance accordingly. So, this is an impedance parameter. So, we have here at the input Zi, which is the self impedance. We have understood this Zi. Okay. Let us see what this equation is. Vi is equal to Ii into Zi. So, obviously, Vi is a voltage which is totaled as two voltages plus something else, which is going to be I0 into Zr. So, it is equivalent to two voltages. What is that one voltage? Ii into Zi. And since Ii is flowing through this circuit, it means that it is the drop across Zi. So, this is Ii into Zi. Another voltage source in series which will have an voltage of I0 into Zr. This is related to current flowing there. So, I can only represent it as a dependent voltage source. This voltage source voltage is dependent upon the output current. So, they come in series because voltage is this voltage plus that voltage. So, the pictorial representation of this equation is what is called an equivalent circuit. So, Vi is summation of two voltages, Ii into Zi. Since Ii is the current in the same port, I can represent it by a self impedance Zi in series with the voltage which is independent of the current through this circuit. It is dependent upon the current through the other port. So, I have to put it as a voltage source. This is the reverse transfer parameter. If this is absent, if it is unilateral, there is no voltage source. So, in the equivalent circuit, if this is absent, if it is unilateral, there will be no voltage source, only this will be there. Now, you can recollect how we discussed amplifier circuits etc., where the amplifier was unilateral, there was no such source at all in those circuits. At the output, we have the equation which is V0 was equal to again Ii into Zf plus I0 into Z0. Again summation of two voltages. So, we have two voltages here, but through one there is a current flowing and that is I0 into Z0. The current in this is I0. So, if I put an impedance Z0, the drop will be I0 into Z0. Next, I have a voltage here which is dependent upon input current. So, again it is a source with a voltage equal to Ii into Zf. So, this is called an equivalent circuit representation of two-port network, any two-port, in terms of Z parameters. What happens if we do in terms of y parameters. This is very simple now. I can quickly go through. I do not have to now put down these equations which you have already got in your notes. We will just put down this in terms of the equivalent. Instead of these things coming in series, now we will have things in shunt. Why? Instead of this VI, we have here II. So, II is summation of two currents. So, the two currents can flow only in two separate paths like this in shunt. Okay. One path will have YI, the self admittance. Okay. Another path will have a current source okay. Another path will have a current source which is going to be equal to something happening here. So, we are going to represent this in terms of dependent variables which are going to be Vi and V0. So, this will be V0 okay, into YR. So, II is equal to Vi into Yi plus V0 into YR, two currents, Kirchhoff's law. That is the first equation, that is represented in equivalent circuit form here at the input. Similarly, at the output we will have a self admittance which is Y0 and a current source which is dependent upon the input voltage which is Vi into YR. So, this is the second equation wherein I0 is equal to V0 Y0 plus Vi YF. Y parameter equivalent. Now, the hybrid variety we have once again Vi and II at the input represented as two voltage sources, sum of one voltage with another voltage, this voltage being HI times II dependent upon input current and this voltage being HR times V0 dependent upon output voltage. This is corresponding to H parameter. That is the first equation. We have Vi equal to HI II plus HR V0. So, I do not have to now put this II, I can just say that it is an impedance through which II flows. So, it is HI times. Here it is going to be now in shunt, this is the hybrid. So, here it is in series, that one it will be in shunt. So, the current source current is going to be HF into II and there will be an admittance here which is going to be dependent upon this voltage V0, this is I0. So, I0 is equal to HF into II into H naught into V naught. So, this is the admittance H naught. This is the equivalent circuit for H parameter. Finally, you can yourself try to draw the other equivalent circuit. It is easy. It will be shunt here arrangement and series here. So, let us see. So, it will be expressing II in terms of Vi into Gi, Vi into Gi, so that I do not have to indicate. So, it is a conductance of magnitude Gi with a current source which is dependent upon the output current here I naught. So, I naught times Gr, that is the current source. Then at the output we have things in series. So, V naught is going to be expressed as a voltage drop across G naught, which is an impedance, and a voltage source which is going to be Gf times Vi. So, this is G parameter. Is this representation clear? It is the same set of equations that we are now representing in the network form. In all these cases, if it is resembling an ideal amplifier, we can clearly see the first thing that has to happen, right, is that all the reverse transmission should go to 0. That means there will not be any current source, it will be open, there will be no voltage source here, it will be shorted, there will be again no current source here, it will be open, there will be no voltage source, it will be shorted. And if you look back in your earlier notes, you will see those are the 4 amplifiers which we had discussed thoroughly without any reverse transmission. Now that we have learnt the equivalent circuit approach for solving any problem on amplifier, let us consider a general amplifier which is now, for example, represented by Y parameters. We know how to represent any amplifier by any one of the 4 parameters, as long as the amplifiers are non-ideal, which they are going to be most of the time, and therefore, we can represent these amplifiers by any one of the 4 parameters. So, let us now see, so far we had not included this reverse transmission parameter in our discussion about amplifiers earlier. So, it was very easy. What is this going to do? This is going to give us a lot of trouble. This is unnecessary feedback from the output. This is going to interfere with our input. Okay. So, how it is going to interfere with our input, we would like to see. So, obviously, the input impedance earlier without this was simply determined by Yi, 1 over Yi, if this is not there. But now, because of this, additional current is going to be drawn, which is dependent upon the output circuit. So, this interference from the feedback, which must be kept small in an amplifier, we would like to investigate, right? How it is going to interfere with the performance of our amplifier, we would like to see, examine. So, Yr is not necessarily 0, but it is kept very small. Even if it is kept very small, how is it going to affect our performance of the amplifier? For that, we can do the analysis now. Same equation is taken, II is equal to Yi Vi plus Yr into V naught. Now, I would like to sort of indicate to you here that I would like to find out what is the input impedance at the input of the amplifier. What is defined as Vi by II. Well, how much is this? This is the input impedance. How to evaluate this? So, we have an equation here relating II with Vi, but unfortunately it has also V naught. This has to be expressed now in terms of Vi, so that this whole equation is a single equation relating Vi and II. That means using the other equation I had to eliminate V naught. Okay. So, let us see what the other equation is. Other equation is, in this case, I naught equal to Yf Vi plus Y naught now. This is the other equation. We have another term here. You just see here. Let us investigate circuit wise. Yf into Vi is the current here. I would like to know what the voltage is here, that is V naught. This is going to be V naught, that I know. There are two admittances. The total admittance of this network is Y naught plus YL. The total admittance of this network is Y naught plus YL. That is being fed by a current source of magnitude Yf into Vi. So, what is V naught? V naught is going to be therefore equal to, this current is going to flow in this direction. So, whereas I have put V naught plus here and minus here. Therefore, there is a negative sign because this current is assumed to be flowing this way. This will be plus and that will be minus. So, V naught is minus of Yf into Vi current divided by Y naught plus YL. This current flowing into a total admittance of Y naught plus YL will develop a voltage which is Yf into Vi, which is the current, multiplied by the impedance, which is 1 over Y naught plus YL. Is this clear? So, this is the output voltage. This will straight away give me what I want, that is V naught over Vi is always equal to, in terms of Y parameter, minus Yf divided by Y naught plus YL. YL is the load admittance. So, this is what we have already evaluated, voltage gain. So, we have now V naught in terms of Vi. So, that is what we wanted here. We wanted to get rid of V naught here in order to find out Vi by II. So, we substitute this here, II equals Yi into Vi minus, because this is Yr, into Yf divided by Y naught plus Yl into Vi, or II by Vi is equal to Yi minus Yf divided by Y naught plus Yl. Please remember this. This is an important relationship. The admittance, okay, this you can call it as Y in, input impedance of the amplifier considering the feedback into account. If Yr is 0, this is Yi itself. So, Y in is equal to Yi minus Yr Yf divided by Y naught plus Yl. In a similar fashion, you can derive the output impedance. What you should do in such a situation is, you should drive the circuit by at the output, okay, with Is. This is the independent source here, this being removed, Is should be removed. So, you are now looking at the output and seeing what is the output impedance, right. So, what is output impedance? V naught, this is V naught, you can remove this, okay, divided by I naught. Okay. So, it is similar exactly like what we have done here. This is V naught, this is I naught. I am applying a voltage here, removing the load, applying a voltage here, finding out what the current is. Then this should not be there. This is so I am applying an independent source here. So while measuring the output impedance, I apply a source here and I will find out the current here. So output impedance is V naught divided by I naught. This is exactly similar to what we had earlier shown you. Only thing is I and O simply get interchanged. So I would like to leave this as a homework problem for you. Show that I naught by V naught is Y out equals Y naught minus YR YF divided by YI plus YS. The circuit that you have to analyze is exactly similar to what we did just previous to this, right? Only that I and O simply get interchanged. L is removed and replaced by S. Okay, that's all. Instead of load, we have YS here. That's all that has happened. But so you can derive this and you will get the Y output. We have derived the output impedance, indicated to you how it can be derived. We have shown what the voltage gain is. I would like you to evaluate the current gain, which is I naught by II. Okay. From the equivalent circuit, I is here. Okay. I want to know I naught, okay, by II here. Okay. So please work this out, and other problems you will see that whether I adopt Y parameter or Z parameter, H parameter or G parameter, universally immittance means immaterial what parameter I adopt. This is called immittance parameter. Whether it is H, Y, Z or G, the input immittance in is equal to Pi minus PR PF divided by P naught plus PL. Right? And output immittance is going to be equal to P naught minus PR PF divided by Pi plus PS. What this means is, if this is Z parameter, this is Z in, this is Zi, Zr, Zf by Z0 plus Zl. Z out, Z0 minus Zr, Zf by Zi plus Zs. So whatever be the parameter you adopt, you will see that the input immittance and output immittance, the nature of this formula remains the same. And this is what I would like you to derive for all the three parameters left out, that is Z parameter, H parameter and G parameter. Show that the input immittance and output immitances are governed by these equations. Okay. That is what can be shown very easily, just as we did it here. These are two sets of equations. You have to appropriately eliminate one of the variables in order to get these different relationships. Okay. So, from this we can eliminate V naught, okay, and I naught is already known in terms of V I. See, for example, here I naught is equal to what? Minus V naught, okay, into YL, because V naught is this, okay, and there will be YL admittance here, and the current flowing in that is going to be in the opposite direction to what we have assumed. So, this is always going to be minus V naught into YL, or we can now say that this relationship is 0 equals YF into VI plus Y naught plus YL into V naught. Or from this we can derive V naught over VI, which we have already done earlier, right, as minus YF divided by Y naught plus YL. That is, from using the second equation and the information that this current I naught is equal to minus V naught into YL, we can get rid of one parameter here, I naught. Okay. So, you get V naught over Vi this way, and that V naught we substituted here and got the information about Yi as Y in as Yi minus Yr Yf by Y naught plus Yl. Now, as a homework problem, you please try to work out I naught over II in a similar fashion. You do not have to now get rid of I naught, retain I naught, express V naught in terms of I naught, okay, and get rid of V naught, okay, and get rid of Vi, and you will get a relationship between I naught and II. In the next class, I will indicate to you, if you try and do not get, I will indicate to you how you can get I naught over II, the result, okay, and also how to obtain Y out. I have given you the method of obtaining it. In case you are finding it difficult to get it, we will work it out again here fully.